Greetings, Mr. Perry here, taking a further look at Miss Van Driska's presentation of forces and the universe. A look at potential and kinetic energy, Newton's three laws, and thermal energy. She says, may the force be with you, but sometimes they're against you. Well, let's take a leap forward and go to where we left off, and the relationship of potential and kinetic energy. Potential energy is energy stored in an object because of its position, that is, where it is in relation to other objects. An example, a ball at the top of a hill has a lot of potential energy. A ball at the bottom of a hill has far less potential than the one at the top of the hill. And we see an example here. The red ball at the top of the mountain has a lot of potential energy because of its position on the hill. Other potential energy forms, gravity potential energy, or GPE. Gravity can affect an object's potential energy depending on the position of the object, and energy is stored in fossil fuels, gasoline for example, and alternative energies, and is released when chemical reactions take place. We look at some energy forms here. We have fossil fuels, biomass, nuclear, and renewable energy. Kinetic energy. Kinetic energy is energy in motion. Examples, a moving roller coaster car, a runner, chemical reactions, changes in states of matter. Kinetic energy can be converted into other types of energy. In a hydroelectric dam, the kinetic energy of the falling water is converted into electrical energy. And some forms of kinetic energy, we have radiant, which is solar, thermal, which is heat, and we have sound, light, chemical, motion, and electrical energies. The kinetic energy of moving particles can be transferred from one particle to another. Have you ever shot pool? Well, you transfer kinetic energy from your moving pool stick to the cue ball to hopefully hit the ball you're aiming at. Let's watch.
Rolling boulder crashing down the mountain. That's kinetic energy. Kinetic. The boulder sitting high upon the mountain. That's potential energy. Potential. Energy in motion is kinetic. Energy that's waiting is potential. But whether it's kinetic or potential, you stretch a rubber band and then release it. That's kinetic energy. Kinetic. You stretch a rubber band and then you hold it. That's potential energy. Potential. Energy in motion is kinetic. Energy that's waiting is potential. But whether it's kinetic or potential, both of them are energy. Olé! The heat that comes when gasoline is burning, that's kinetic energy. Kinetic. The energy that gasoline has stored up, that's potential energy. Potential. Energy in motion is kinetic. Energy that's waiting is potential. But whether it's kinetic or potential, both of them are energy. Olé!
Well, potential energy can transfer its energy into kinetic energy and vice versa. As we see here on our diagram, at the bottom of the hill, we have a roller car, which is sitting, and it's not moving, so it has zero kinetic energy. Well, it gets pulled up the hill by an outside force, we'll call it, gains potential energy as it moves to the top. At the top, it has maximum potential energy, which is transferred to kinetic energy as gravity pulls that car down the hill. And once it hits the bottom, the process repeats itself, and we start all over again. Take a look at this.
With their high speeds and bright colors, you may find it hard to believe that roller coasters have been around for more than 200 years. But since their beginning, the basic science behind roller coasters has remained the same. It's the science of forces, energy, and motion, called physics. Like any other amusement park ride, roller coasters need energy to work. But it's what happens to that energy that makes roller coasters unique. First, the cars of a roller coaster are pulled to the top of a steep slope by either a chain system or another machine for pulling and lifting, called a winch. These machines need energy to work, but this energy doesn't just disappear. It is changed and given to the cars of the roller coaster. What is this energy changed into, and how does it go from the winch to the cars? An object sitting still at the top of a hill has stored energy due to its position. This position gives it the chance or potential to move down the hill, and so we call this stored energy potential energy. As the cars of a roller coaster are pulled up to their starting position, they are gaining potential energy. The higher the cars are pulled, the more potential energy they gain. And once there's enough potential energy, the fun begins. As the coaster cars zoom down the track, their potential energy is turned into another kind of energy. If potential energy is the energy of position, what do we call the energy of motion? Kinetic energy. Both this potential and kinetic energy rely on a fundamental force of the universe, the force of attraction between all things that we here on Earth feel most strongly as the downward pull of gravity. When roller coaster cars go over the top of the ride's first hill, the force of gravity pulls them downwards, turning their potential energy into kinetic energy. And as the cars climb the next hill, the kinetic energy is turned back into potential energy, which is then released again as kinetic energy, and so on. Alternating between these two types of energy makes for an exhilarating ride. Now the next time you ride on or see a roller coaster, whether just going up and down hills or spiraling through turns at 60 miles an hour, you'll know a little more about how physics is turned into fun.
Potential and kinetic energy. Kinetic energy can change depending on the mass and velocity, or speed and direction of an object. How do you increase kinetic energy? Well, kinetic energy is related to an object's mass and speed or velocity. The heavier an object is, and the faster it moves, the more kinetic energy it has. Kinetic energy, mass, and speed. Well, our formula for kinetic energy, mass, and velocity. On our left, we see Ke, or kinetic energy, which is on the top of the triangle. On the bottom, and we have our divisor line between there, we have M for mass and V for velocity. In our basic formula, we have Ke equals 0.5 times the mass times the velocity squared. And we look at our units. We have mass, which is measured in kilograms, and we have velocity, which is measured in meters per second. And we have kinetic energy, which is measured in joules. Remember diamonds. Well, how do we use the formula triangle? Well, we write what part you're looking for. Which one are you supposed to find? If you're looking for m, for example, you would put the ke on the top, as you see in the triangle, and you would put the velocity on the bottom. Conversely, if you're looking for velocity, then you will put the ke on the top, and you'll put the m on the bottom, and just plug your values in. Let's look at an example: kinetic energy, mass, and velocity. The problem: a car with a mass of 700 kilograms is moving with a speed of 20 meters per second. And we look at our triangle up there. We have ke, m, and we have 0.5 times velocity squared. Which one are we looking for? We're looking for ke, which means our formula is 0.5 m multiplied by v squared. Our numbers, let's plug them in. We already have the 0.5. Our mass is 700 kilograms, and our speed is 20 meters per second. But remember, our speed is not just 20. It is because v squared, we have to do 20 squared, which is 20 times 20. And doing the math, we come up with ke equals 140,000 joules. Let's continue with energy and forces. Remember, energy equals the ability to do work, and work is when a force applied to an object moves the object in the same direction of the force. And force is the energy in the form of a push or a pull that changes the motion or shape of an object. Energy and forces, well, forces give energy to an object, causing or stopping motion or changing an object's direction. Forces that are balanced are opposite and equal in size and cause no change in motion. And unbalanced forces cause a change in motion. Why? Because one is stronger than the other. Balanced and unbalanced forces. Balanced forces equal forces that act on an object from opposite sides. The object doesn't move. There you are, you and your twin, and you're pushing and you're about as strong as each other. The object doesn't move. And we have unbalanced forces on the bottom here, and they are unequal forces that act on an object from opposite sides but make the object move. And there you are with your little brother, and you're pushing, and he's pushing, and he's stronger than you. No, he's not stronger than you, and you win because the forces are unequal. So there you have it, our third segment of Forces and the Universe. You got a fair amount of work to do with this. Let's get it done.